What?
We're not going to do all the details, but we are trying to walk through the method. This one is doing a convolution of a table function. Looks like this. It's called T1U. What is TU? Such a T1U convolve with T1U. Let's make it really simple.
What's
2, 1, negative 2, 2, 1.
Can you just do a superposition, break that down into two functions?
You could do that.
So
Is that what we're gonna do?
yeah, we can first write T1U as 2 parts, right? There will be a rectangular U minus another rectangular that's shifted. So it becomes this minus this. Is that what you're saying?
I was actually thinking about summing, but it's equivalent.
Oh, okay. Oh, yeah.
Like summing the first one. So
Or you're saying like do this.
just one.
Because you need to phase shift both of them. It's supposed to phase shift in one of them. But you get the summation, so you get rid of a negative sign.
One question. Yeah.
It's either that or this plus this.
How do you encode width
Width of what?
of the rectangular function?
Oh, I did not.
Okay.
Oh yeah, I didn't write down the correct form. Just try to express the idea.
Cool.
So and then convolution. Do you follow? If we call this, if we do this one, I think this one is easier because that one is something that is twice magnitude and one. This one we call it T11U. This is T22U. T12U. So we have T11U plus T12U. Then T1.
You still need to phase shift T1.
No, I think
Where
you
is the
define
magnitude?
T11 to be asymmetric.
T11. Just asymmetric. So
Yeah.
this is call this thing T11U.
They're different amplitudes?
No,
But
they
same
have.
amplitude. They're all one.
It's just that one goes from -2 to 1, and the other
Yeah.
one goes from -2 to 2.
Okay. So this is minus 2
Oh,
to.
I can see that now.
Yeah. So how does it work? That the convolution of summation of two things. It follows linearity, right? Is that correct? Does it follow this rule?
Yeah, it's commutative, right? A convolution.
It's just an integral, so yeah.
Okay. Like this?
I think so.
Was that the case? Maybe what I did.
Well, okay. First and third terms are for sure correct.
Mhm.
The other one is really just is it
Is it
F
twice?
F convolved with G the same as G convolved with F, right?
It is.
So then that's right.
Okay. I trust all of you. Because I forgot. So this is actually not too difficult to find the convolution of this, but then there's actually a more difficult part, which is to find the bin pattern of TU. If you want to do it from, if you find TU first, then find BS, it's hard. But if you find BS of each component, then linearly.
That's where Sydney was saying is actually useful, is that you can define that as a centered rectangle.
Right.
And then
with a phase shift.
Yeah.
Yeah. So T11 becomes a rectangle convolve a phase shift, a delta. So that becomes even more helpful when we deal with it.
Yeah.
So what becomes a T11 convolve T12 if T11 is a rectangular convolve something?
Use distributive property.
Okay, that's a table we can look up. But I think that's like a procedure to solve this problem. If we first identify the building blocks of this function, and then because it's asked us to find BS, the bin pattern of a very complicated function, we can find the bin pattern of individual building blocks, then add them up or convolve them or multiply them.
Yeah. I guess it's easier to do leave that also. I think that's what you're saying, right? To leave everything for Fourier space, and you just do multiplication there.
Mm-hmm.
That's Did they ask for T1 convolve with T1? Is that a solution?
That's
Okay.
the question.
The question was asking first part this, second part find BS.
Because if I didn't need to do that, I would just find that. Oh, actually, I wonder if that's helpful. So what if I didn't know what that was? Because that's hard to do.
Mm-hmm.
So the first thing I did is I actually moved everything into frequency space, and then I went backwards after I was done doing all this convolution and addition, and then I found T1. Because this term especially looks kind of like it might be hard.
Yeah, that was what I was asking. If you just do pretty much everything, do everything in frequency space, you don't do the kind of avoid that multiplication there, which seems nasty.
And the phase shift just becomes an exponential. So
yeah,
I think that's good. I have not thought about that way. Or we should try it.
Yeah, we should.
Do you want to write out the solution?
Yeah.
Or
yeah.
Then send to everyone.
Mm-hmm.
Okay. Cool. Okay. I think that's this exercise. That there's another one calculating equivalent beamwidth, but we haven't calculated beamwidth here. It's just going to be messy.
Mm-hmm.
But however, this is the step that you can either break it down to basic elements, so we don't do the complicated one. Then we multiply them, add them up to get the final beam pattern.
You mentioned Parseval, right? That shows up when you do 3 down beamwidth or something like that, right?
Parseval just says that the total variance, I guess, the total energy is the same. So if that's actually the end of my sentence. But the reason I brought it up earlier is because if all of the energy is pretty much between -1 and 1, because mathematically, all the mathematicians would start jumping up and down about infinity and 1 being the same.
Mm-hmm.
But that's the...
Oh yeah.
I'm not good at finishing these sentences. I'm done.
We understood.
Yep.
No, I was just saying because I don't know if later on you define 10 log of the absolute power of the beam pattern squared. That's often what if you look at sonar specs, that's often what you'll find.
Yeah. I did not write that down in the sheet. I think I should have.
And I think that's when Parseval's theorem will come in.
Yeah.
That's what I was trying to get at. Because for instance, when you have that type of plot.
Yeah.
Oh yeah, the Parseval rule that all the energy and the beam pattern is equivalent to that of the table function.
Yep.
Okay. So here,
These plots. Remember?
I know what that is, but I don't know what does it have to do with the thing.
It has to do with like when you try like some of the definitions have involved this main loop, and that's pretty much like doing the integral of 20 log or something like that. 20 log of
Oh, yes.
yes, the magnitude of the beam pattern.
okay. Here is a more complicated version of the text practice. So we know that if we look at a graph, we can know what that's a table function. If we look at a graph of table function, then we can decompose it into individual components and then find the beam pattern. But sometimes we can also be given a numerical representation of the table function, and then from that we have to figure out the beam pattern. How to recognize what a numerical function is in terms of those building blocks is another exercise. So let's go back to the discrete array that we were talking about. That we knew a taper function. Like a rectangular taper function. That convolve. Is it convolve? Multiply, sorry. Okay, multiply by these discrete delta functions will give us the discrete version of the array. Right?
Yes.
And then this is written as the rect u, the offset. This one is written as the summation of delta u minus n delta u, the distance between them, delta u.
Mm-hmm.
And what we have here is h summation n minus 1 over 2 . So basically what it does is this set a range. This is infinite, meaning, and you when you multiply them, you cropped some of the delta functions out,
Sure.
right? And that gives us the discrete the beam pattern of a discrete array. So here, if I give you this function,